Okay, thanks. Okay. So reaction kinetics is kind of two things. Like I'm reading this, it is kind of I think of reaction kinetics as how fast a reaction occurs, but actually can't remember which unit it is in, whether it's unit 2 or unit 3 in this class. But we're actually going to at some point not only track how fast a reaction occurs, but we're going to kind of peek around the curtain behind the scenes and look at maybe mechanisms by which a reaction occurs. And when I say mechanisms, a mechanism basically is kind of a series of steps. That's what a mechanism is. So reaction kinetics, I think both involve rates and mechanisms. So a reaction rate, if you're like me, I usually think that like in the lab, you go over there and you mix two things together and they just react. It's like done, ta-da. But it's not always instantaneous. There's a delay. There is a speed with which the reactants do their thing to form products. So in this part, we're going to talk about how quickly or how slowly a reaction occurs. Okay? And the thing is, you can either measure the reactants going away, or you can measure the products getting formed, okay, to check your reaction rate. Okay, so reactants go to products. We're going to use a big R for reactants, a big P for products. So over time, as long as it's not a chemical equilibrium with like an arrow that also goes from the right back to left again, as long as it only goes one way, like I'm shown here, you would expect the reactants to go away over time and the products to build up over time. Makes sense? Here's one for you. The speed at which a chemical reaction occurs, and we'll talk more about why this is, but it slows down over time. The longer the reaction proceeds, it goes slower and slower. So one way to show that mathematically is to say that time is inversely proportional to rate. Time is inversely proportional to rate. Now we talked about inverse and direct proportionalities when we talked about the variables in gases. So this is to say, as time goes up, rate goes down. Okay? It's hard to imagine as time goes down, rate goes up. That would be going backwards in time, yeah. So we can switch that up if we want to. And we could say rate is inversely proportional to time. So the rate at which a reaction is occurring at a given moment is proportional to 1 over time, or inversely proportional to time itself. Reaction rates slow down. So when you see an R, think reactants. When you see a big P, think products. How fast does this occur? Well, here's some data. Not so surprising. So this is time is equal to 0. So when you first start your reaction, we have all reactants, no products. So just some numbers thrown at you. Actually, you're going to see these numbers plotted in a minute. Okay, you let it go 5 seconds. Okay, not so surprising, your reactants went down and your products went up. You guys remember what the bracket means, right? It means molarity, molar concentration. Okay, so 10 seconds, 15, 20 seconds. So you can definitely see the trend in your reactant is getting, your molar concentration of your reactant is getting less, the molar concentration of your product is getting greater. So graphically, this is what that would look like. Oh, we'll talk more about a K later, rate law constant. So the red is your reactant, the molar concentration of your reactant. The green is the molar concentration of your product. Okay, that works. So reaction rates, the rates. So reaction rates are, I feel like I almost we haven't seen it here in a minute, but the rate the reaction is occurring is we can track the change in concentration of your reactant. Get it? Change concentration of your reactant over change in time. Let's look at what we have here plotted, okay? Notice what we have along the y-axis is concentration. Along the x-axis is time. So this is the slope of what I have here. The slope of the line. Does that make sense? So what I'm trying to say, because I was thinking about this in my office, and I'm like, so m is equal to delta y, change in y, over change in x. Change in y. Well, that is, depending upon if you're looking at the red or the green line, pick on the red line, that's the change in the concentration of the reactant. Delta x, change in time. Okay? So on this graph, if we draw that blue line right there, that's a slope. Does it look like a slope? That's a slope, just that segment from, this is 2-second intervals. Okay, so from 0 to 2 seconds, that's the rate. That line right there. Another segment, so this would be, from 4 to 6 seconds? That's that rate there. You get the idea. And here's the rate between 10 and 12 seconds. If I were to show those three together, can you see where the slope is changing? It's getting flat, it's flattening out. Okay, and actually that is the rate getting slower and slower. Okay. And here is clear out here, okay, time-wise. So you're going to be doing some homework problems, and you might be asked to find the rate between time intervals of 0 and 10 seconds. Okay? This is what you'll be finding, and that's fine. Is it real representative of an instantaneous rate? It's an average rate. Okay? And some of you may be familiar with, I'll get to it here in a minute. And this would actually be the overall slope from 0 times equals 0 to 30 seconds. What I started to say is the best slope is actually a line that's tangent to the curve at any given time. So this would actually, if this line is tangent at 10 seconds, this would be your best slope, instantaneous slope at 10 seconds. Okay, but we're not going to do tangents. We're going to kind of go with averages. But that's what you're calculating when you calculate rate. All right. So, to track the rate, you track either a reactant going away or you track a product being formed over a particular time interval. Okay. And actually, we've got some data we can do that. We're going to go back and revisit that data we had on the table a minute ago. So from the time segment of when it first started, t is equal to 0 to 2 seconds in, to 5 seconds in, we can use that data to come up with a change in concentration of the reactant over a change in time. Change in concentration of the reactant is that it's always final minus initial. So at 5 seconds, it had decreased to 0.121 moles per liter. It started at 0.200. So these are going to be negative, aren't they? So that's the change. And of course, the time interval, it's always final minus initial, but it's definitely 5 seconds. So the change in the molar concentration of the reactant over that time interval is the the rate of the change of that reactant is 0.079 moles per liter divided by 5 seconds. Rounded to two significant figures. I guess this should have said 5.0 seconds. Round to two significant figures, it's negative 0.016 moles per liter second. Your reactants are always going to be negative, the change in concentration of your reactants. All right. You could look back in your notes or that original table a few slides ago, and you would see for that same time interval, maybe surprising, maybe not so surprising, that actually the product went from 0 to plus, or sorry, it went from 0 to 0.016 moles per liter. Or no, it didn't. It went from 0 to, and then divided by 5 seconds. Yeah. What'd you say, Andrew? Yeah, thanks, 0.79. Yep, then you divide it by 5 seconds to get this same change in concentration of the product, but it's positive. And actually, I think I have a note here that this is only kind of neat how this worked because the stoichiometry actually is 1-to-1. Okay, we're going to actually kind of have to mix it up here in a minute, and it won't always be 1-to-1. So you could do that for the other intervals, from 5 to 10, from 10 to 15, from 15 to 20. And hopefully you're seeing what I said about it slowing down. Now, if you're like me, you have to you see the numbers and you have to concentrate what that really means, right? But it's actually going slower. In this case, the formation of the product is getting the moles per liter per second, the molarity per second is decreasing. Okay, and this is also slowing down. All right. So yeah, so this only happens because the stoichiometry is 1-to-1. So these aren't, I'm going to have to kind of clean it up here. These are an indication of rate, tracking the change in concentration of a reactant or the change in concentration of a product. They're an indication of rate, but rate always has to be positive, okay? And rate has to be the same number regardless of what you're tracking. So we have to kind of remove the effect of stoichiometry, basically. And we're going to do that. It's always something. Okay. So real rates are always positive. Actually, so how do you make something that's negative always positive? What are these? Absolute. Yeah, absolute value. Yep. Or I think in some of my notes I say, if you know it's negative, to change in concentration, for instance, of a reactant, if you know it's negative, then go ahead and take it times -1. So, okay, so instead of R going to form P, we now have a few other variables. We're basically saying A will go to form B and C, but the stoichiometry is 2 parts A will go to form 2 moles of A will go to form 2 moles of B plus 1 mole of C. Okay. So if you pick on, like the slide says, if you pick on A and C, you can see that it takes 2 moles of A to make 1 mole of C, for instance. So when you come up with their change in molar concentrations of A and C, they're going to be different. We need to fix that. So working with some real numbers here, let's go ahead. And anytime you see that little subscript 0 on the molar concentration of A, that means initial. So A0, molar concentration of A at time 0. Okay. Of course, it's going to decrease after 25 seconds. It's gone down from 0.1 to 0.060. So we could come up with the rate of change of A. Okay. We're going to do that first. And then we're going to do a bit of stoichiometry and come up with the rate of change of C. So here's how that looks. So the rate of change of A, not too bad. We said it's final minus initial. the final was 0.060 moles per liter. The initial time zero was 0.100 moles per liter. And then the final time was 25.0 seconds. The initial time was 0.0 seconds. Subtracting and then taking the ratio. So subtracting, you get the negative 0.040 moles per liter divided by 25.0 seconds, rounding to 2 sig figs. The rate of change over that interval for A is negative 0.0016 moles per liter per second. Rate of change of A. So that answers the first question. Rate of change of A. Now we're supposed to come up for the same interval, the rate of change of C. So basically, we need to find what the concentration of C was at time zero. What was the concentration of C at time zero? 0, right, very good. And we also then need to know how much C we had formed after 25 seconds, okay? So after 25 seconds, do you buy this, that we had reacted 0.040 moles per liter, or excuse me, yeah, moles per liter, or moles of A per liter. Do you see where that number came from? That was your change in molar concentration of A. And then we need to just pick up, this is what we did in Gen Chem 1. Go ahead and introduce a stoichiometric ratio with the coefficient of C being 1 and the coefficient of A being 2. So if that is the moles that reacted, then the moles of C formed then would be actually basically 1/2 of that. 0.020 moles per liter at 25 seconds. 0.020 moles per liter of C. Now you probably know what's coming next. To get the rate of change of C, we take final minus initial. So that'd be the 0.020. My notes really probably should say, to keep it clean, to keep it 100, it should say minus the initial. You guys told me the initial concentration of C was 0. Divided by the time interval, 25.0 seconds. So it looks like this. Okay, so the rate of change of C was positive over that same interval because it's a product. And it was 0.0080 moles per liter per second over that same interval. So you have A and then you have C. The rate of change of A, the rate of change of C. So here they are side by side. Notice I've gone ahead and applied the absolute values of. So that means that instead of being negative, that the value for the rate of change of A is 0.0016 moles per liter per second. So these differ by a factor of 2. Do you guys see that? Factor of 2. So here's what we do. Okay. The way you basically fix the effect, it's the second blue right here. The way you basically fix the effect of a stoichiometric coefficient is not only do you take the absolute value of the change in concentration of a reactant or a product, but also you divide by the stoichiometric coefficient. If the stoichiometric coefficient is 1, guess what? You're just dividing by 1. The stoichiometric coefficient in front of the A was 2. Okay, so to get the real rate, we have to divide the rate of change by 2. So that's how that works. Okay. So over here, don't miss this. This basically says the real reaction rate. The real reaction rate. okay? We can track A, B, or C, but if you track A, you have to take it times -1, or the absolute value, and you have to divide by the coefficient, which is 2. Another way to say that is you multiply by 1/2. Okay, so that's where that 2 came from. The real rate, if you're tracking B, okay? If you're tracking the rate of change of B, that's fine. You don't have to do anything, take it times -1 because it's a product, it's increasing anyway. But you have to divide by the coefficient of 2 or multiply it by 1/2. It's the same thing. The real reported reaction rate, if you were tracking the change in C, guess what? Wouldn't have to do anything to it. You could report that as the real reaction rate. So regardless of you tracking the change of A, change of B, change of C, it's got to be the same reaction rate. And this is the way it's done. Makes sense, I think. Okay, so the reaction rate in the example we looked at where you were given information about the concentration of A at 2 times, the real reaction rate would be 0.0080 moles per liter second. Okay. You knew I was going to get to it. Or do you guys have an assignment slide there?
No,
I do.
We have a lot. Okay. We have more slides. Are we skipping them?
We're going to come back to those slides. So we'll finish up those slides, but in the meantime, these are great to do hot off of what we just talked about. See, and we're still getting out early. Let's take a look at them. And I did have time to go ahead and put these little hints together. So I'll push those out there. Okay. So one looks like this, where you basically have A and B going to form C and D. And they give you information about A, which has a coefficient of 2 in front of it. But they say the rate of change of A is, and it would be negative, right? 2.0 times 10 to the -4th moles per liter per second. Okay? And they want to know what the real rate of the reaction is. So this is what, this here in kind of blue and green is what we were talking about. The real rate is the change in either the reactant or product divided by time, and then also divided by the stoichiometric coefficient, or times 1/2 in this case. Okay. So it's not too bad. The next part, what is the rate of a disappearance of B? And so what I did was kind of take this sort of thing and I kind of rewrote it. And I basically said, if you want to know the rate of change of a reactant or product, you just have to take the stoichiometric coefficient times the real rate that was given. So that's probably what I would do there. And recognize, since B is asking for B, which is a reactant, it's going to be negative. Make sure you apply that too. And then for kind of a similar thing for D. For C, I said CB. So basically it's a product and you get to use the coefficient of 3, right? So 3 times, to me, the rate is what I would do. There's different ways to work that, but as long as you get the right answer. So for this one, you'll need to use this figure. This figure is where hydrogen peroxide is breaking down into water and oxygen. So the red line is the real line, okay? And the blue line, they're just trying to show you a line tangent to T is equal to 1200, which now I've got a different idea how to do this. But the first question, question A says, how fast is it going here at this point right here? And I don't know. What I said is, to me, I need to get a slope there, right? And so I said, well, I would just take, where it says green, I would take those 2 points on either side of it. I don't know. T is equal to 1200, T is equal to 400. pull off the molar concentrations and come up with a rate of change there. And once you have the rate of change, of course, the coefficient is 1, so you don't have to do anything there. And then it says, and to me, this was even easier. I don't understand. B's not too bad. It says, what is the rate of the reaction at the time which, well, maybe it is, because you still have to rate of reaction, sorry. What is the rate of the reaction when you have only 0.5 molar hydrogen peroxide? So you go over here. So basically, you need to do a rate here. So again, you can take on either side and come up with a slope right there. The next one is just dealing with a reactant. It's going to form some miscellaneous products. And it gives you the molarity at 2 times. Notice it doesn't give you at time 0, just kind of at 71.5 seconds into it and at 82.4 seconds into it. What's the average rate of reaction? So this one, it gives you the concentration of A initially, after 1 minute, and after 2 minutes. And I put little subscripts there for time 0, time 1, and time 2 minutes in. And so you're supposed to come up with what is the rate from 0 to 1 minute, and what is the rate from 1 to 2 minutes. So, and then why aren't they equal? And just kind of in general, it's supposed to slow down over time. See if you find it slowing down over time. And for the last one, again, we have 2 reactants going to form 1 product. They give you information about the rate at when the molar concentration of A is 0.3580. And you're supposed to come up with what would be the rate of formation of C at that time. And I think you can just use a stoichiometric ratio. But what do I have for the next one? All right. And for B, okay. So for B, it says, based upon the rate that you came up with in, based upon the rate that they gave you, the 1.6 times 10 negative fifth moles per liter per second, what will the concentration be a minute later? So just read my hints. And then C, my brain is fried. Okay. But kick them over, and basically what we talked about this afternoon should get you down the road to doing well. All right? All right. Have a good weekend.